I want to welcome everybody to this evening's meetup again. It's a PP and AI Swiss meetup. Today we'll talk a little bit more about artificial intelligence in industrial applications. And I'm happy to welcome Christopher Ganz today. Hi, Christopher.
Hi, now it's on mute. Hey, Stefan.
Welcome. It's a pleasure to have you here on board today.
Pleasure me.
Since we just in the beginning for your lecture, I would like to a little bit introduce you as a person. I found it quite interesting that you have been so much involved into innovation. That's correct?
Yes, I do have quite a track record in the most of my career in ABB, all across the innovation value chain. I mean, from research, R&D, product management, technology strategy, all of that was involved in the ABB service strategy, was involved in the ABB digital strategy, and most recently I was part of what was called ABB Future Labs, an organization where we looked into future trends, future market trends, future technology trends. I did that for the CTO. Now, unfortunately, ABB got rid of the CTO, the CDO, and all their teams. So therefore, I'm now working on my next career, which is partly and still to be decided, going into some advisory in these topics that I have been working on, and I'll touch on several of these topics in this talk today.
That sounds quite interesting. Thanks for just being part of it today. A few organizational remarks for everyone who just joined us today. If you look down to the navigation bar, you will find there's a Q&A section, which is actually or can be used if you have questions. And please just use it throughout the lecture. So Christian was already so kind to ask us if you speak English or German today. Yes, it will be in English, will be recorded. And just please be free just to ask your questions during the sessions. I will take care of them. I will ask Christopher during the session presentation other questions you have, and we try to answer them directly during the presentation, sometimes even in the end. So let's see how much questions we do have here. The subject is quite interesting, Christopher, AI in industrial applications. What can we expect from this day today?
I will touch on some industrial applications, and there are some very specific boundary conditions in industry. I'm not talking about the enterprise level where an industrial company is similar to any other kind of company. I mean, you have orders, you have customers and all that, but I'll talk about more about the plant side, production site part of it, and we'll dive into some of the challenges and some of the findings that I had in my work in ABB, and also since I'm now on garden leave, I expanded on that and did some further work, and I would like to present this as well, which might lead to a discussion then in the end on how to address these challenges, because not for all these challenges we have solutions today.
Yeah, I can imagine. Sometimes people think that innovation, hey, that's cool stuff. Yeah, it's the nice part of a business, and you can think about new ideas. But you have definitely some organizational challenges to overcome, and I guess you will cover that in your presentation as well. You might have seen people that I started a short quick poll, to a little bit understand better who you are and what kind of level of interest you have. Just as a summary, Christopher, for you to understand as well. Half of the people are just new to industrial AI, maybe partly also to artificial intelligence in general, and we have half of it are advanced. So we have a good split between novice people and advanced people. Regarding the professions here in the match, that's also quite interesting. 30% data scientists, about 30% software engineers or architects. We have even some product managers here, 11%. And from business, we have 30% of of participants. I think it's a good mix for us also to take care a little bit on the technical side and also the business side during the presentation, because the mix of the people just is perfect. So welcome again. And yes, Christopher, take the floor. I'm really looking forward to what you have to tell us about applications in industrial AI.
So now, as we checked before, I hope you still see this. And now again, I'm looking for my mouse. Anyway, should be working. Okay, as I mentioned, I will talk about AI in industry, in industrial applications. Now I really need to. Oops. Okay, I will look into some industrial applications. I will then put some light on a focus on a special area where I think it's underexplored today, engineering, and then I'll give an outlook with basically some challenge that is currently not addressed, and then finally come to conclusions. So when we start with the industrial applications, let's have a look at some of these industries, like, for example, the oil and gas industry. Quite many processes that we're dealing with are pretty dangerous. If something goes wrong, then you might get killed, or the environment gets severely polluted, or you can create damage that is easily costing you an awful lot of money, not only in damaged equipment, but also on missed opportunity. Some of these plants very quickly have downtime cost of $500,000 per hour. So you'd be rather careful on what you're doing. What's also particularly in process plants like this, like chemical industry, these plants have long life cycles and have also long run times. I'm originally coming from power generation, and the power plant might well run 2 years uninterrupted. So you can't go there and tell the customer, hey, you need to shut down the plant for a software upgrade, because shutting down the plant takes 4 hours. Restarting the plant might take 4 days. And during that time, you cannot not generate revenues. So it's really important that you know how these plants operate and what you're dealing with. What is also the case in many cases is very high energy, or pretty high energies. So these energies have to be controlled. They have to be controlled in a safe way, because if they are getting out of hands, as I mentioned, they can create a lot of damage to equipment, but also to people. So today, many plants are run by automation systems. And these are pretty much always the same. They have sensors installed. In some plants, it's thousands of sensors that measure pretty much everything that you need to control. Then they analyze the signals, and in the end, you put some action back to the plant. And there, between the sense and the act, you have the physics of the plant. And I think that is one aspect that we're dealing with. We're dealing with the physics. So automation is measuring things, is analyzing, and typically it's analyzing what is different from what I expected it to be. And then you have some actuators, you have pumps, you have valves, you have conveyor belts, you have robots, whatever. And then you act on these so that they put the plant at the state where you want it to be. That is state of the art currently of an automation system. You have these control loops, which are either continuous, so this type of loop, sense, analyze, and sending the signal back to the plant happens continuously. Typical cycle times are 1 second, half a second, 100 milliseconds. And very fast ones might go to microseconds when it's about electrical systems. Or you might have discrete control loops where you have a triggered event, for example, when a tank is reaching the full sensor, then you open a valve so that it gets slower, or other discrete events that trigger an action then that interfaces with the plant. So the key here is you're dealing with the physics of the plant. So you are interacting, you're sensing the physics, the reality, and you're acting back on the physics. And the plant has some process limitations. You shouldn't move it too quickly. The speed of the reactions are defined by the physics. You can't go faster or slower. Particularly the reaction time is in some cases required. So you need to have a reduction time that is twice as fast as the slowest, as the time constants that you're controlling. So the physics defines what you're doing. Challenge here, you might have a potentially high impact of these very quick decisions. If you have 10 of these control loops executed per second, there's very little time to react. And then, like for example, in a power plant, if you're going over the maximum speed of the turbine, you have more or less 4 milliseconds until you have to cut off the power to the turbine. So it's pretty fast. If you don't react that fast, you're running into problems. So what does that look like? Today, the critical safety relevant processes, you have this dangerous area there where a false negative, if you don't detect what's going on, even you don't detect one single dangerous situation, you're in trouble. So you design the system so that it covers a little bit more than what's absolutely necessary to be dangerous. So you rather define a larger coverage space around kind of better safe than sorry, and you shut down a few more times than it would be necessary to really prevent danger, but better rather not miss one of these dangerous events. The false positive. So if you're detecting something that's actually not there, it impacts the plant availability, which is of course not good, but at least nobody gets killed. In the non-critical, where you're improving the effectiveness, the undetected event is less critical because today these tasks are done by operators. So humans that sit in front of the screen and act on the plant, and they run the plant up and down and think this is the best way of operating it. If you have an optimization system that is supporting the operator, anything that you do is better than what the operator can do. So if you miss out on a few opportunities that the operator didn't see either, you're not worse than today, but whatever you detect is better than what the operator has today. If you are actually improperly detecting, if you're providing false positives, you don't do that too often, and the operator is no longer trusting the system. And honestly, we have supplied a few of these systems, optimization systems, where the operator quite quickly said, well, it doesn't really help me. It gave me the wrong recommendation, and I no longer use this system. So this nobody is perfect approach. The system can just be a little bit more perfect than the operator, but it should never be less perfect than the operator. So given today's capabilities of AI, where you cannot guarantee the reaction of a system, particularly when it's outside its training set, I would not recommend to use it in a critical environment as the last resort for reaction. However, the non-critical, to improve the effectiveness, that is actually the place where we're seeing AI solutions being applied today. Of course, you can take care of that in some way. So AI in industrial systems has to be looked at in the context of the plant. So there's today still always an operator there, and AI is mostly used to support the human. Very good examples are perception, image recognition, video, sound recognition, and all these, where you can tell the operator something that he cannot see or grasp with his senses. That those are very good use cases. Data interpretation, large plants have 7,000, 10,000 signals. To figure out what's going on is pretty tough. And if you can have AI to kind of cluster data, manage alarm, which one was the most important alarm and all that, and then still leave the decision to the human, that this is a good area. Condition monitoring and failure prediction is also good because it's very well suited for the fundamental functioning of a neural network. You have a set of input data, but basically the measurements, and you have the result is the device okay, or is it not okay? It doesn't have a direct impact on the plant, because once you see that something is not going well, you still have the maintenance crew to look after it. You can go to that device that the system tells you is faulty, and confirm the finding of the system. What is typical in such situation for such a system, that it permits overrides. So a human can always say, well, yeah, fine, I see what you're saying, but I still think something else is a good reaction to this situation, and can override the AI system. So there's a question around be more concrete, and I'm sorry I can't do that, because very often we don't have the release from the customer to use their names. So yes, we have seen that, but very often it has not been cleared for communication.
Is it possible to have a context which is not company specific, so to say, was that kind of setting where we did that, or experience that support human stuff? Is that possible?
The advanced perception we did in a number of areas. One was to detect in ports these danger labels on trucks, so that the truck drives into the port, and immediately you get an alarm when there's something dangerous on there, so you don't have someone sitting there. Data interpretation, alarm management, yes, that we implemented into the standard system, so that is now available in a number of installations. Condition monitoring, perception, prediction, I am aware of some cases for motors and some cases for drives. These are all things that are part of the portfolio of ABB, and they are supplied to whoever is signing up for these contracts. Where the AI interacts with the automation system is, for example, in production optimization, that you optimize the system. A implementation where you don't really trust the AI system, but you still would like it to interact with the plant, you can build that in such a way that you monitor kind of boundary conditions. And then as soon as the AI system is leaving the boundary of safe behavior, you switch back a maybe less optimal but safe control law that takes over from AI, brings the plant back to a safe state, and from there you can restart the AI. In any case, There's a safety system as the last resort, and this is something that not even the humans can override. So the safety system is there to also protect the plant from wrong behavior of the human. So that is very, very robust. It's constantly monitoring the plant for an unsafe state. And whatever is happening, whether through a failure or improper handling of the plant, be it through the human, be it through AI, it switches the plant off. You still lose the plant, but you can restart and it's not damaged. So safety systems are a really important concept in that context.
If I look at your overriding rules you just mentioned in the two cases, is it correct to say that in the human context you believe that the danger for a machine might be too intense, so that we have to switch to humans? And in the automation case, it's better to have the machine, so to say, to control the process, because human might be more prone to fail, or is it wrong?
It depends on the application. There are, and also on your typical situation in a plant. As I mentioned, in a power plant, where I'm coming from, in the German plants, you had engineers running the plant. So they demanded to have overrides over the automation. They said, well, we can handle a critical situation better than the automation system. Still, the safety system you cannot override. In other places, the demand from the plant owner was that no, I basically hire my operators from the street, and they can just see that something's going wrong and then call the supervisor. I don't want them to interfere with anything. So in that case, the humans were not allowed to override. The safety system you should never ever override. There was one very, very famous case where this was done. It was Chernobyl. The engineers took the safety system away because they thought they can handle the situation. Mm-hmm. That is something that is fairly difficult. But of course, if you're an expert, you can do that. And I know a colleague who destroyed the turbine by overriding the safety system.
I think that's quite interesting, but I've never seen the kind of distinction as you did here. Yeah. It's cool for me, just to better separate the cases. But what I get more and more understanding of is organizational and business implications of it, in terms of working with colleagues who don't give up control or don't want to give up control, and the conflicts that might come out of that. So it seems to be a huge area of discussion.
So there's a question, examples of sensors that are being used. Process plants, typically they measure physical properties, temperatures, pressures, levels, all kind of levels, flow, whatever you can measure in such a plant. You have sensors. Typically you have sensors for safety applications. So you want to make sure that the plant is in the right state. Other sensors you need to make sure that you can, for example, if you again coming back to the turbine example, the temperature at the outlet of the turbine is a very critical variable. So you have two ways of influencing the temperature. One is you can blow more air into the turbine. The other one is you can blow more gas into the turbine. So you control that temperature very carefully. So you measure it constantly in these cycles. And as soon as the temperature is too high, you reduce the gas. You give more air. As soon as it's too low, you give more gas and reduce your air. And you do that constantly. So these control loops, you have hundreds of these. Some control pressures, some control levels, some control temperatures. It really depends on what you want to do. A chemical plant has totally different sensors than a power plant. That is typically defined by the use case.
Thank you for answering.
So as usual in machine learning and AI, data is the key problem here. garbage in, garbage out. I guess you all know that. And when it comes to data, industrial applications are somewhat special. We are seeing many applications of AI dealing with consumer data, personal data. What you put into Google, into Facebook, and all that is being analyzed. Reason for that is because your behavior, the companies would like to assess your behavior. Your behavior is pretty unpredictable and not really controlled by any physical laws. So therefore, you need to resort to data-driven algorithms and make sure that you get some kind of understanding how the average person is behaving in such a situation. In industry, it's very diverse. I've had some discussions with IT companies that told me, well, there are billions of sensors in the IoT, and you have tons of data. Well, yes, we do, but some of this equipment is custom built. For example, a large power transformer, you get a specification from the customer, and that this is built exactly 5 times for this one plant that has 5 transformers. Similar, some other heavy equipment, sorry, other equipment is produced in larger numbers. Now, thanks for the tip for getting the water. Other equipment is produced in larger numbers. For example, motors, drives. Those are produced by the 100,000 and millions, but they're installed all over the place. So a customer might have 4 motors of the same kind, and another customers might have a few hundred, another customer might have 2. So on every site, you have relatively little data from any device there, and it's not really comparable. You cannot compare the data you get from a robot with the data you get from a medium voltage switcher, because these two behave totally different and have totally different types of data. Now, I get the question about the ethical dilemmas. I would like to park that question to the very end, because that's pretty separate discussion that we can take later on. So
I'll keep that in mind, and I will ask the question in the end. But as we can see, Christoph is fully aware of what's happening from the question side. Perfect, Christoph.
Okay, so you have a very diverse population, and you should actually know what this population is doing, because this has been designed by engineers. So the physics of a robot is pretty well defined, and we know pretty well what that robot should be doing when it's operating normally. So we are actually interested in what we don't know. And here I have another challenge here. The data is, we collect tons of data, terabytes of data. First of all, the data is just reflecting the physics. So if a plant is absolutely running correctly as designed, then we know why the signals are the way they are, because we designed it that way. So another aspect is, if a plant is running steady state base load, the power plant, the refinery, these plants might run for months on the same set point, always producing the same amount and the same quality. So you look into the plant today and you see a set of temperatures, pressures, and material flows. You look into it tomorrow, you see exactly the same data set, tiny little variations. You look into it the day after, in a week from now, you always see the same information. So you do collect a lot of data, but it does not contain any new information. And with information, I normally go back to the definition by Shannon in his information theory back in the last century. And basically he explained, the account for how much information is in your data is how surprised are you by that data. So in the curve to the left, you look into the plant, it's behaving always as designed, and you're not at all surprised to see it that way. You are surprised about that spike that I have there in red. That's the interesting one where you want to cycle in. Why did that spike happen? So when we look at the distribution of the data that is measured, we see that the big part of the data is describing normal operation. More or less the center of the Gaussian curve is how the plant was designed. There's some variations depending on the environmental conditions. It might deviate from that a little bit. It might deviate if a different type of product is produced, but normal operation, you pretty much know that because you designed the plant in that way. What you don't know is failures, where the plant is going to the bad side, and you're also interested in where did the plant work exceptionally well. Maybe an operator put a different set point there, maybe something else was changed, and you would actually like to repeat that. So you would like to reduce the failures, increase the golden badge there, and therefore move the average to the right. In many consumer applications, you're actually interested about the average. You don't really care for the extreme individuals. You care for the big mass of the people, because that is where you want to sell your products or influence the population. So we have quite a diverse goal here for industrial applications and consumer applications. Just to give you an example here, if you already know how the plant is behaving and you're seeing these measurements to the left, this is the sensor readings. Let's say if you have a model of the plant, which is basically the way you know the plant is using, you should actually use that information to really get to the data that you don't know. So here on the right, I have put the information that's kind of a subtraction of the measurements and the model. And you see there towards the end of the series there, it starts to increase, which you don't really see on the raw measurements. So if you're just training your AI system on the raw measurements, you will pretty much prove physics, and that is known. So you need to calculate out of these measurements everything that you already know, pretty much how you designed the plant, and then the data is revealed that is not according to the design. And that's the interesting part, because a failure might be exactly starting there, where the plant starts to deviate from how it was designed. To summarize this section here, yes, we're seeing quite a few good examples in games, very well-defined rules, limited set state space. Pretty much you will never see a figure on the chessboard that you don't know, and you will never see a figure that is moving in a way that is not according to the rules, or you will be disqualified immediately. As you probably know, a chessboard is a reflection of a battle, and everyone knows battles that have gone in pretty strange ways and have been decided by fairly non-intuitive behaviors of the combatants. And preparing for the slide here, I looked into like, for example, how Waterloo was lost, and on that in that reading, I realized that Napoleon was indeed a bad chess player, but I'm not sure whether being a good chess player would have helped him.
I don't know if you've seen, but Christian Pittel had another question.
Yes, always good. Unbalanced data set.
Christian, you can speak if you like.
Yeah.
If you have a right to speak, maybe you can explain your question for a second.
Hi, I'm asking about the unbalanced situations, because as you said before in your previous slide, you was mentioned a lot of normal situation and just a few abnormal situations that are on interest. So how do you treat that data? Because for modeling on machine learning, you need to, or it's better to get a balanced data set. So probably in this case, you need to focus just on these spatial situations. And how do you model for this? Maybe using an example in time or in timeline or something like that.
Well, there are. You're right. You actually put a lot of effort into collecting the interesting data. Now, another problem is that industrial devices have been designed to last very long. So you don't want failures. And we put a lot of effort into designing equipment that lasts uninterrupted or shows very little failures. So therefore, you need to increase your sample set. You need to cover more devices. So you need to collect information from motors from all around the world so that you catch some of these special cases. And then there are some cases where there are databases of failure cases. And then there's also, again, with the failures, you know some indications of upcoming failures. For example, in motors, you know that if we're looking at the frequency response of the motor, you know certain frequencies should not appear. So as soon as one of these appear, then you need to look at it. You start collecting data and then you analyze it. But it's a very hard problem. It's a very hard problem.
Thanks, Christian, for the question.
Okay, I will dive into an area. I've so far covered the operations, but today we mostly see it in operation and mainly in maintenance. But the industrial plant lives a longer life cycle. It starts from designing, and a lot of the performance of a plant is actually defined when it's being designed already. Once the plant is built, the performance is set. As I mentioned, the plant behaves as built. So if you build it in the wrong way, it behaves exactly the way you build it. So it would be interesting to use AI and optimization approaches for the design phase. But then if you really need to have a lot of data to train your system, you can't build a lot of plants to really get the data back. The time constant is just far too long, and you don't build so many plants there. So therefore, so for process industries, the engineering loop cycle time is decades. You build a plant, and the next plant will be built in 30 years. Discrete manufacturing, if you're building a new type of car, the plant will be re-engineered partly. If you're building a new type of drug, the machines will be reconfigured. So in discrete manufacturing, you have shorter life cycles because the plant is reconfigured once you want to produce a new product. In power plant, you always generate power. So here, the key is to be able to simulate. And in many applications, simulation is today one of the standard tools, but that could actually be exploited to create these optimized plants. And I do have an example here that is actually tied to another interesting technology. More and more we are seeing that, I mean, the traditional way is you have a designer, you get a spec, that blue document up there. I'll come to that question about the plant. The design is given to the designer. He's simulating that, he's getting the KPIs, how it's behaving, and then he's doing that over and over and over again until he reaches his KPIs. In his mind, he has human build capabilities, and you build the product how you would design it. A new generative design approach takes a simulator, calculates the KPIs, and then trains the AI on these properties. And similar to the Go game, the KPIs are kind of the outcome of the game, and you learn how to play the game against the physics of the device. And then you get very strange looking objects that fulfill the specs. And the reason why we can do this now is also because of 3D printing. Now we can build these things and create this type of wild thing. For a human, it's very, very difficult to design something like that. But the AI-driven, the generative design solution would actually come to that solution there. To the previous question, if the plant is not behaving properly, why don't you change the plant? It's pretty hard to change the plant. And the example I gave was, if you design the plant wrongly, it will behave wrongly, but you shouldn't do that, of course. I mean, if you really build a plant that is not working properly, then you're in deep shit as a plant builder. So you shouldn't do that. And of course, you can fix some problems in the plant, but I mean, the whole plant is very difficult to change after it's been built. Another example here is from, yeah.
You just go back to the previous slide for a second. Yeah. I love the term generative design, yes, and I saw some examples in the past. Do we have some examples which you can tell us?
I just noticed examples, can give you examples from literature. I mean, one from I know from ABB was that the colleagues designed magnets for motors.
Yes.
Because normally you have magnets that are square around because they can be manufactured very well. They found a way to print them and now create magnets that are better suited for the electromagnetic field. I know example from Airbus. They have designed this stupid thing. I mean, the little wall between the cabins, that is a solid plastic wall. They've redesigned that to only contain the structural elements within, and then put cloth or thin plastic on that. And that then in the end looked like a tree leaf, very fine structures in there that you wouldn't find out that this works. Another one also from Airbus, the step for the pilot to enter the cockpit, two steps of metal, normally thick aluminum plates. They were redesigned. There are now two very, very thin plates with some very fine structures in between that actually increase the strength of this plate. You can reduce the weight a lot, and particularly when less intuitive properties are being optimized, like for example cooling capability, you get very good results.
I personally, when I saw the example from Airbus, I saw that in the past as well. I just stick with the idea that it's possible that a machine comes up with a solution which a human probably wouldn't find.
Absolutely.
This is the fascinating stuff of it, and it will have a huge impact on some parts probably of engineering. This is something of major interest. Thank you.
Yeah. So going further, putting different products together to build a system. Siemens had this problem here. They had, it's an aircraft electrification system, and the best solution known today is patented by Honeywell. So what you do as R&D, you need to find a way around that patent. So they said, let's describe all the components. Let's describe how they behave when they connect. And now let's use such an AI-based optimizer. And it worked. The system found a solution that is actually the perfect solution too bad, the perfect solution is the one patented by Honeywell. So they were able to prove that, yes, the perfect solution is the one from Honeywell. So the system was able to reproduce that solution that Honeywell's engineers had come up with. It didn't really help Siemens to find a better solution, but it worked, and it probably works in other cases there. Now, for these kind of activities, you need a lot of information other than just what you measure from the device. So you need the product type, like the drawings, like the design things. You need the information, how it was built, when was it built, in which factory, how was it tested, how did it behave in the test. You need the system's context when the device is integrated into the system, like, for example, these motors. Is it driving a pump or a fan? Is it within the plant? Is it exposed to weather and all that? And then in the end, you have the operations context, and you can measure the condition. And in some of these examples that I've just shown, it doesn't help you to have the condition only, because a motor, for example, that's installed in a conveyor belt, you cannot compare to one driving a fan, even though it's the same motor. So you need to have its application. And that information is typically stored somewhere else. So here, what actually helps is this concept of digital twin. And digital twin, as we have defined it also in the Industrial Internet Consortium, is any digital reflection of a physical asset. And it's important that you actually make that available to every other user of a digital twin, because maybe you need to know some of these aspects of the equipment. And then that, having the data associated with this one piece of equipment, is actually crucial for training an AI system, because there are situations where one motor is removed from a pump, is replaced by another one, and the removed motor is repaired and put in the inventory. So you need to distinguish between the motor as a driver of that pump and the motor as an individual with a particular property of operation. So you can then arrive at fairly complex data situations when dealing with the equipment on site. I would like to dive into some questions that I had recently when writing a paper, when it was triggered by someone writing about how AI will take over the world very soon. And I came to the conclusion that probably not so quickly, because the one thing how humans learn is mostly around asking the question why. Now, those of you who have kids, I don't have kids, but I have a little brother, smaller brother, who always come back and say, why? And this why is actually the source explaining causality. So you ask why, you get because, and the cause, so you can make your own link between a cause and an effect. And you learn that, you learn the cause and the effect. And that is something that's missing in current machine learning approaches. The causality is the one thing that needs to be in the training set, so it has to be given by the human. It cannot deduct the causality from that arises from that question why. And I think how humans are then putting together all these cause and effects is that we build a network internally, a knowledge network, so that in the end we can answer a question why, where we have never ever seen someone telling us because, but we can actually trace back through that network to arrive at something that we know. And in many industrial applications, causality is really crucial. If you're coming to a plant that doesn't work, the first question you get, why? So I think this is a research direction that should be followed to really come up with the explainable AI and to be able to answer this question why. I leave this open. I don't have a solution for that. I'm just putting you this to this community here. Some conclusions. I always keep saying to whoever wanted to do an AI, I want to do an AI project. What are we doing in AI? AI is just a tool. What is really the problem you want to solve? And maybe there's a much easier solution to your problem. Number one. Number two, do you have the data? And in many cases, well, first answer was, of course, we have data. We have tons of data. Then you look at the data. One customer once told us he wants to build a motor monitoring, a motor diagnostic solution. And we asked him, okay, well, you have data? Oh, yes, I have all the data going back decades. Turned out that he had ERP data. When was the motor bought? When was it installed? When was it sent back to for repair? That doesn't really help you. You don't really understand how the motor is operating. You need to have the vibration data. So you might have a lot of data, but you don't have the information that you need in the data. Second problem we found, that tons of data that people had was inconsistent, incorrect, incomplete. So I think there are studies around that say AI, in AI projects, you spend 80% on getting the data right, and the 20% you get on the algorithm. Second bullet here, machine learning has particular difficulties in exploring areas that it wasn't trained on. It can interpolate, it's not very good at extrapolating. So you have to know that. You have to know that if you're leaving the space that was covered by the training set, you don't really know what you get. Going back to the safety question, wouldn't use it there. Since I touched on engineering, good simulation might be able to produce the data that you need. You can simulate process variations. You can simulate some effects. But then if you have a simulator, you can also use quite a bit of other tools. And what I also have to say is a good simulator does not come cheap. So simulation would be important. In simulation, there are also a few unsolved problems. In the end, what I think is a way how it can be integrated in the end by interacting between humans and an AI system, kind of creating an augmented expert combining best of both worlds. So there is a question, a concrete example of a situation during which you ask why. Tries to find the real reason. Maybe you unmute Frank.
Yeah, we can ask. Here's 3 questions open. We can talk about the questions in a second.
Okay.
I think we invite him. Frank, be prepared. I invite you to speak in a second.
Maybe the last question on the why first, because that's related to what I've just talked about.
Okay, thank you. You're invited. Hi, welcome, and thanks for all your questions. We have actually 3 which are still open. Can you just clarify the last one, please?
Yes. So it's from innovation. I know this method, five whys method, and I've learned that it's quite effective to find out what the real reason, what the real cause for a problem is. That you have the problem and you continue to ask why until you find the real reason. I was wondering if you could share an example with us.
Well, just look at the condition monitoring example. Your AI system is telling you this motor will go down in 2 weeks. So it might be a fairly complex device. In another talk this week, I gave the example of a system where we diagnosed a gas turbine compressor, and the system was telling us you have a problem. Challenge there is, if you really have a problem in the compressor, you need to open the machine, which means you need to have to fly in a team of specialists. Opening the machine takes about 5 days. Fixing the problem takes another 5 days. Closing the machine takes 5 days. So your plant stands still for a month or 2 at an hourly cost of $250,000. So you'd rather be sure what you're actually gonna do, and why did the system come to the conclusion that something is wrong. Because for a decision of that consequence, pretty much shutting down a third of that country's power generation, you would have to explain that to some expert and then to their management. Why are we going to lose so much money right now? So very, very often the typical situation is you have a situation, you want to take some actions, and in critical plans you have to get it approved by the shift supervisor. And this guy would ask, okay, why do you think I should shut down now? Why do you think we should increase temperature there? So it's very often the very first question that is being asked.
Frank also had two more questions, one about the ethical dilemmas and one about the management. Let's start maybe with the management part.
You moved the management question away.
I can ask it here again.
Yeah, sure.
To answer this. But Frank, you can also just, if you like, can take the floor again. So,
yes. The management question. So very, very interesting what you shared, the examples, and what I understand is in many situations are relatively high risk and a lot of cost. So I suppose security, safety is very important. I'm curious to know, to be very specific. I read about the term psychological safety, and I understand this is of huge importance. So that people have psychological safety to talk about problems, to talk about what is not working.
Absolutely.
How is management done to enable that people can talk about problems?
That is a really important part, and in industry, it really depends on the culture and on the type of plant. But I can give you another example that I know from a friend of mine. He's a fighter pilot in the Swiss Army, and he's also an airline pilot. And what he says is that in the airlines, this culture is deep into the organization. You cannot be blamed for the mistake, because we learn from the pilot's mistakes. You always get a debrief. You always have to tell what went wrong. You always have to tell the bad situations. He started a new business in training doctors in surgeons in the operation room. And there, very often you have the professor who is the god above everybody else, and nobody really can question his decisions. While in the airplane cockpit, the co-pilot can question all the decisions of the captain, because he might have overlooked something. So what he did was he rented a cockpit simulator, and he put these medical teams, split them in two, put one team into the cockpit, the other team on the ground. And the guys on the ground pretty much had paper and instructions. He made sure that the team on the ground had all the information to safely land the plane. And then he put the other half of the team in the cockpit, and the key learning was that they have to collaborate, and whoever has the information has to guide. So typically he found out there where the professor was in the cockpit, it totally failed, because he would never ask anybody for his advice. So it's really partly it's the culture of the industry. In some industries, it's the regulations, and it's also the culture of the country. Some countries are more open to having subordinates questioning the boss's behavior. Some other countries are definitely not. But it's a very good point here. If you I mean, as an operator, you pretty much you sit in the control room for 2 years and nothing at all is happening. It's boring. And then all of a sudden, worst case, you get 150 alarms at the same time. The alarm bells start sounding, you get a red flashing light on the screen there. Maybe you're on the phone with your boss that complains that you haven't filled in your timesheet last month. And all of a sudden, you know something's going wrong and you have to figure it out. You have people on the plant with walkie-talkies running around, and you know that you have maybe 5 minutes to resolve it. It's a lot of stress. So your psychological safety definitely plays a role. And there is an ABB team in Sweden that is designing control rooms, and they have put a lot of effort into the design with lights that change depending on the severity of the situation, and physical, so moving the desk in an alarm situation that you have to stand because they figured out that you're more alert when you're standing. All these things. I think it's underestimated. I think there could be more research on that, but it's definitely an important topic. Yes. The ethical dilemmas. I have to say I was in a panel earlier this week organized by Orgaling for the European Union, who wants to regulate AI. And from the industry, we figured out that it's a little bit far-fetched for industrial applications, because you have to, I mean, there's always this explanation, well, the autonomous car is driving towards an elderly lady and a woman with an infant, and you cannot brake, and which one should you run over? I always say, how many times has it ever happened on Earth that you came into such a situation and you had a choice? If you are in a situation that you can no longer brake, your car is probably uncontrollable, and you just run over wherever the car is going, or you panic and you steer wherever. I think this is really a niche problem. If we agree that you shouldn't kill people, we're dealing with that problem all the time. As I mentioned with the safety systems, these systems are put in place that nobody gets killed. And we have tons of regulations that tell us how do we have to design systems so that nobody gets killed. And I emphasize the word system and not a technology. And this was also in the discussion on this week. Yes, AI might not be safe enough to use in a critical situation, but maybe it can help you there. And maybe you put a safety belt around it where the system takes control to really prevent it from doing harm, while when it's behaving normally, it can run in whatever way it likes. Similar to what we built around the human, we cannot assume a human to react reasonably. Maybe he panics, maybe he presses the wrong button, maybe he's out smoking a cigarette. So even for humans, we put these safety systems around them to avoid that somebody is getting killed. So we have tons of regulations that define how we build industrial systems where nobody gets killed. So these kind of dilemmas that the robot shouldn't kill anybody, yeah, sure, we build that into our system all the time. I mean, we don't want to be in the press to build robots that kill people. Another interesting aspect is what's frequently being discussed is bias. I mean, you have these reports that some AI systems qualified women in a different way from men, and you figure out that women react differently to vaccines than men, but you only have studies on men and all that with race and all that. If you really look at industrial data from machines, I don't have a problem with bias. I don't have a problem if a Siemens algorithm is only dealing with Siemens devices. Maybe they're different. Maybe this is a service that is only offered to Siemens customers, and ABB needs a completely different type of algorithm because the ABB robots are built in a different way, and the KUKA system wouldn't really work. And then also, yeah, what's wrong with offering a software solution to only the customers of ABB motors? It makes the motor more valuable. If you then realize that you have only covered pulp and paper motors and you cannot cover motors that are built into conveyor belts, then you have a quality problem. Then your conveyor belt customer will complain and say, well, your bloody software doesn't work. And then you have to fix it. So it's a liability issue, quality issue, like we have others where things don't work as expected and the customers ask us to fix it. So I think for industrial applications, I think the ethical dilemmas are built into the regulations today. I'm not saying that they're not there, but I think we have decades of experience how to deal with it. I think to put the focus on industry is moving the focus away from the areas where we really need it, in the areas where we're actually treating personal data. And that I think is much more critical than what many people think. If you look at the Cambridge Analytica case and all that stuff, I think there are some issues that we have to deal with. But I think industry is not really the first place where we need new regulations, because we already deal with quite a lot of regulations.
Thanks a lot, Christopher, for all these deep insights that just shared with us today. Fantastic. For anyone who would like to connect with you, it's obvious you're on LinkedIn. People can connect with you on LinkedIn. You're on Twitter, which is remarkable. I like that.
not for very long. I was at a conference last week and somebody asked me, do you have a Twitter account? And I said, actually, no, but it would be a good idea to have one. Now I have one.
You're reactive, you change things. Yes, that's good.
Yeah,
good
sure.
stuff. I want to say thank you to all the questions, Christian and Frank, for asking the questions during the presentation. Thanks for all of you having been part of today. Christopher, it was just awesome. A few organizational things again. This session was recorded. I'm going to upload the session. And can you just share the presentation with me? I can upload it as well.
I will do.
That would be fantastic. You might have heard some clicks sometimes during the presentation. I was doing some screenshots, uploaded to the meetup page. So you will find yourself present there as well in some ways.
Okay.
And yeah, thanks guys. And I know it's different time on your side. Sometimes it's morning, sometimes afternoon, night, sometimes even late night. I wish you a nice evening, nice day, whatever it is on your side, in your time zone, and hope to see you again. So I say goodbye and stay safe in Corona times. Yes.
Stay healthy. Thank you very much. Have a good time.